Hi, welcome to this lesson on number patterns, finite geometric series. In this lesson, we're going to have a look at the second formula of a finite geometric series. So in the previous lesson, we learned how to do the first formula for a finite geometric series. We used a little bit of logic that was similar to Gauss, and we did a bit of a multiplication, and we started matching pairs and cancelling out. So we're going to do the same thing here, setting up equation 1 as just the sum of the first n terms, t1 plus t2 plus t3 plus t4, all the way up to the nth term. We're going to multiply both sides of that equation by r, and we match it as similarly to what we did in the previous lesson with the first formula. So here we get ar squared, ar cubed, all the way up to ar to the n minus 1. And then this additional term ar to the n just comes from multiplying this term by r, and you're left with a times r to the n minus 1. Okay, but what we did is we did equation 2 minus equation 1 for the first formula. This time we're going to do it backwards. We're going to say equation 1 minus equation 2. So on the left hand side, it's going to become Sn minus r times Sn. And on the right hand side, these grouped terms are still going to cancel with each other, just like they did. However, when you get to the very last term, so a r to the n minus 1, a r to the n minus 1, those will cancel. But now you're left with a minus a times r to the n. So that's what we have on the right hand side here. So on the left hand side, I can group out Sn as we did, and now we're left with 1 minus r. On the right hand side, we can group out a's, and I'll be left with 1 minus r to the n. So the goal is to get Sn by itself. So I'll divide both sides by 1 minus r, and I thus get the formula as seen below here. S sub n is equal to a times 1 minus r to the n over 1 minus r, where n is a natural number. So let's look at the similarities in the first formula. So the first formula, it was S sub n equals a into 1 minus r to the n over 1 minus r. So if you look very carefully, these look very similar to each other, and they should be because it's the same formula. It's just that inside the brackets, instead of 1 minus r to the n, the first formula was actually written like this. Let's be a little more careful there. So it's r to the n minus 1 over r minus 1. So that was the first formula that we derived. And again, now if you look at the similarities, inside the first formula brackets, it's r to the n minus 1. But inside the second formula, it is 1 minus r to the n. So essentially, it looks like the signs had just swapped. And that's actually correct, because if you pull out negative 1, that becomes r to the n minus 1. If you look at the denominator term, this is r minus 1, and this is 1 minus r. But 1 minus r, if you pull out a negative 1, just becomes r minus 1. So when you divide 1 minus r to the n over 1 minus r, it's the same thing as dividing this right-hand side here. But negative 1 divided by negative 1 is positive 1, and you're left with r to the n minus 1 over r minus 1. So it actually shows that this expression here, which was used in the second formula, is exactly the same as this first expression here used in the first formula. So the question is, well, why do we need to do it two different ways if it's the same formula? Well, just like in the first case, this was used better when r was greater than 1. This one is best used when r is less than 1. Because what happens? So let's say if r was negative 3, that becomes 1 minus negative 3, which is 1 plus 3, which is 4. So why do we really have two different formulae? Well, it's just because we really like positive terms in the denominator. That is the only reason the second formula exists. By pulling out a negative sign, it's just so that when you work with your r values, your constant ratios, if it's greater than 1, it's easier to use the first formula. When it's less than 1, it's easier to use the second formula when you're plugging in. All right, that really does come down to personal preference. Either way, whether you use the first formula or the second formula, both should still be valid, regardless. This best used is just so that by convention we have a nice positive denominator. It's not that it is necessary. It is just that it makes the sum cleaner when there's a positive denominator. All right, so if you decided you wanted to use the first formula when r is less than 1, by all means, you're still going to get the same answer because of this algebra that we've just shown here. Okay, but just by convention, that's what happens in mathematics over thousands of years as we create more and more mathematics. Conventions start to set in, and then that's the way we generally like to do it moving forward. Okay, I'll see you in the next one.